the next presentation I will give myself. I will show you a portable station for QO-100 assembled from components from the AMSAT-DL shop. So the down converter, up converter, the modified LNB, and this will give us about it will take about 45 minutes. So we should be on time, hopefully, to then also be able to enjoy our lunch. This block diagram shows the principle of the whole transverter. We have a 10 gigahertz LNB, like everybody is using, the AMSAT-DL down converter with the integrated GPS module, and an up converter to generate the transmit signal. Externally, there is a GPS antenna module, very simple antenna, active GPS patch antenna, and we can also connect the 1.3-inch Oled display to it. From the LNB, we get the two downlink signals from the wideband transponder and the narrowband transponder. Wideband transponder being horizontally polarized. It needs 18 volt provided by the down converter. And what we also do, we provide a 28 megahertz reference frequency to the modified LNB generated in the down converter module. The narrowband transponder is vertically polarized, and we supply 14 volt to switch the right polarization. The down converter converts this signal down, and then number one provides a wideband output at 1130 megahertz, where you can connect a Datv receiver. It also provides 10 megahertz reference output. In my case, I'll be using that for locking the ICOM IC9700 to it, and the receive IF of the narrowband transponder is chosen to be 145 megahertz. The down converter module can be changed to different IF frequencies. I've chosen a downlink on 2 meter and uplink on 70 centimeter, because you will never have your harmonics in the TX falling into the receive path. So 70 centimeters uplink in, up converted by the up converter to a 2.4 gigahertz signal going to the patch antenna. The output power, normal output power, is about 3 watts, 2.8 watts. The whole setup is running with DC voltage between 9 and 15 volts. And we have some auxiliary ports like the PTT input and communication port output, where we can monitor the parameters of the up and down converter. I'll come to that later. If we look on how this hardware looks like, the same block diagram now with the components. The LNB from AMSAT is a modified Opticum LTP04H. So modified so that it gets the reference frequency from externally over the wideband output. We use the AMSAT-DL down converter and the up converter. The feed I've chosen is a Porti feed, a patch of the year, with a patch antenna for transmit and a circular waveguide for the receiving on 10 gigahertz with a Venton rocket, because I'm using an offset dish, and for offset dish with higher F2D, it makes sense to add a lens to focus your beam and optimize the radiation pattern of your feed into an offset dish with an F2D, say, higher than 0.4. The assembled module looks like this. I put it in a box, which is actually something I found in my drawers. You see the OLED display in the front, and yeah, that's essentially all. The modules are in one of this, in one of such a box. The frequency scheme, the precise frequency scheme, is shown here on this slide. The wideband output from the LNB, when it's operating from 24 megahertz reference frequency, is 1132.5 megahertz. The down converter is really routing this signal out again to the wideband transponder output, so that you can connect your Datv receiver. I'm using a mini tuner directly to this. The narrowband transponder output is at 1129.5. And as I mentioned, this is down converted to 2 meter. GPS input 1500, the reference frequency output, and of course the transmit output. The down converter with the GPS module is also providing the reference frequency to the up converter. So you have a small interconnection, and this 40 megahertz signal is used by the up converter to precisely up convert the 70 centimeter IF to the 2.4 gigahertz signal for the uplink. Everything is GPS locked, and in the down conversion, I've actually made some small modification or add-ons to the original set. I'm using a splitter to split the 2 meter down converted output, either directly go to an SDR, or before I go to my IC 9700, I've added a 30 dB attenuator. This is number one, the gain of the LNB and the whole down conversion scheme is pretty high, higher than really a normal radio needs. So attenuation here does not really degrade your receiver performance because you have so much gain in front. And if I'm unintentionally transmitting in the RX output, this attenuator is capable of handling 100 watts. So I've tested it. You can never damage your down converter, even if you are making a mistake. In the up conversion scheme, similarly, we have two inputs. One is a TX input with a low input power. About -4 dBm is sufficient to go through a combiner into the up converter and generate this 2.8 watts output power. And for the IC 9700, I've also added here a 30 dB attenuator, additional limiter, and a small attenuator for leveling the power to have the same input power here from the TX in low input and the high input. Nominal input power from the IC 9700 is 1 watts, but also here, if I unintentionally transmit with 100 watts, it's absorbed in the attenuator, and the rest is limited to 10 dBm by the limiter, so nothing can really happen when you're, for instance, in the field and something goes wrong. So these are the levels, the nominal TX input levels I mentioned, -4 dBm from the SDR input, or 1 watt 30 dBm from the IC 9700, attenuated, limited, and finally the input of the up converter is -5 dBm, which gives 34.5 dBm output power. The absolute TX input levels are really 100 watts on the ports which are connected to the transceiver. At the TX in low input, you can have up to +7 dBm, 5 milliwatts. So you have a range of more than 10 dB, go over the nominal range without creating any damage to the up converter. If we look on the, this is a measurement of the whole up converter, and you see that the input is at 430 megahertz. I've used the TX in low port. This is the numbers you see in here. P in is at the TX in low, and you see the output power here, the output power and the gain. And here you see the current consumption. The 1 dB compression point of the whole chain is a little bit less than 2 watts. The saturated output power is 38 dBm. There's also a table you will see in the presentations which will be published if you are interested in some more of the details. Interesting, the efficiency of the whole transverter when you go close to saturation or in the higher output power range is a little bit more than 20% power added efficiency. So this is the front plate of the encasing where the transceiver is in. So you have the TX in low input port from the SDR. About 1/4 of a milliwatt is sufficient to drive the transverter. We have the TX in high, the PTT input to key the transmitter. Actually, you can also run the up converter all the time. You can make a short here and run it. It only saves you a little bit of power, but it's running full duplex anyway. So if you don't want to use a cable to your transceiver, you can just have here ground this, and you will have the PDT on all the time. The OLED display is showing you here, for instance, the GPS data, your QTH locator, the time, and then also whether your transceiver is in a good shape. So you see the output power of the IF, the receive IF is in the 2-meter range. The LNB is supplied with 24 megahertz. We see 12 satellites are locked and the precise latitude and longitude information. The communication output is a serial output where you can show various operating parameters in a remote display. You will also, I don't know who is a member of AMSAT-DL, but if you have seen the latest journal, we also have some information about how to use this COM output port, for instance, by a web server, and then you can monitor your output power, various conditions, including the GPS information. We have on-off switch, we have the power input 9 to 15 volts, and the narrowband IF output here. Actually, on this picture, there is one connector missing, which is the narrowband IF output for the SDR, which I added later, so I missed that on that picture. On the back side of the transverter, we see the wideband input, where we get the signal from the LNB at 1132-ish megahertz. We see the wideband IF output, so that's internally routed through. Here you can connect your mini tuner or whatever you prefer to receive the wideband signals. We have the narrowband input also coming from the LNB, the GPS antenna input, including the phantom feed, the 10 megahertz reference output, which I'm using, for instance, for locking my IC 9700 to the transverter. And this is the output for the transmitter going to the PuTTY antenna. Yeah, just another picture. The encasing I had on hand has a large heat sink, and all the components, you will see the inside a little bit later, are mounted on this heat sink. Though there is no need for a fan, with the efficiency we have, it's fully sufficient. Also, if you have it in the sun, to run it without any active cooling. This is how I mounted the transverter on my dish. I've mounted the arm for the feed upside down. You'll see some details later. And so the cable from the output of the up converter to the feed is only about 40 centimeters. So very little losses. And so it's quite convenient to have it there. Yeah, this is the bottom part. And now we look inside. You see here is the up converter part, which goes to the antenna port for the PuTTY. This is the down converter part. Here you see the attenuators. I show you some details later. Power splitter, limiter, and then the front with the display and the user interface. Same picture the other side. I'm using mostly a semi-rigid cable or semi-flex cables because of the nice shielding. Or if I use flexible cable, double shielded cables are recommended. Here you see how I mounted the up converter to the heatsink. I'm using a copper spreader, so a copper plate under the up converter. Between the PC board of the up converter and the copper spreader, there is a thin layer of thermal conductive material, which is flexible, but it brings all the heat from the PC board, or most of the heat from the PC board, down to the copper spreader, and so the up converter stays pretty cool. The down converter is also mounted directly onto the heatsink. It's not absolutely necessary to mount the up and down converter into a shielded encasing, but I prefer this to make sure there is no unwanted intercoupling or something. So I've put everything in shielded boxes, even though there is the metal encasing outside, of course, also shielding the whole setup. There's a picture with the two boards opened. You see in the down converter also the GPS module, which is plugged on, and the reference frequency output. There is a second reference frequency output, which is unused but terminated with a 50 ohm resistor. And here is the up converter board with the power management, DC-DC converters. Here you see left is the input, some filters, drivers, and these are the final stages for the power amplifier with 90-degree hybrid shifters, which makes the PA also quite rugged with respect to a mismatch at the antenna port because of these 90-degree hybrids. If there's a reflection, it gets absorbed in those resistors. The two TCXOs on the GPS board, as well as on the down converter board, it's not shown here, but I have put additional foam inside before I put the lid on. So this insulates these TCXO in addition to make it very thermal stable. It's no big deal, but I recommend to do this and to make sure that the TCO drift is minimum. You know, the short-term variations are determined by the TCXO itself, the frequency variations. The long-term is locked by the GPS. The GPS loop from the GPS into the TCXO by the PLL is very slow. So it takes several seconds to lock. And therefore, short-term variation would be still visible on your output signal, or you can see on your receive signal. So some thermal insulation is not mandatory, but it helps. This is the 30 dB power attenuators, which I built. I had them still on hand, and I used some surplus Teflon PC board, cut it, and it's just 50 ohm input-output traces. And those are used, as I mentioned, at the IF output of the receiver and the TX input from the transceiver, so that I cannot harm accidentally the up and down converter. The 30 dB insertion loss is pretty precise and 2 m/70 cm, and also the input return loss is very high. So this also helps you because your transceiver will always see a perfect output match, so no problems can arise by mismatch of the transceiver. This is the RF limiter I've been using. I also have this still in my drawers. This limits the input signal to plus dBm, 10 dBm. So the input signal is first attenuated by 30 dB by the bigger attenuators. And then the rest is limited, power limited by this kind of diode limiter. It's suitable for a frequency range up to 3 GHz, though I operated at the 70 centimeter band. Insertion loss is pretty low. And once you exceed a certain level, then you see how the clipping of the signal is happening. Of course, then you also see some harmonics. But if you operate it at a nominal input power of 0 dBm, the harmonics are below 60 dB under the carrier, and only if you increase it into the unwanted range, which is not nominal, then you can see that it limits at about 9 dBm, and so it's pretty close to the spec. The power splitter is a standard mini circuits power splitter. You can use different ones. This one is pretty small. And I've put 2 of them in the box, one to split the receive signal and feed it, number 1, to an SDR and simultaneously to the transceiver. And the same is true for the transmit path, where I combine the input signal from an SDR and the transceiver to the input of the up converter. The insertion loss at 2 m/70 cm I measured also to be very low, about 0.3 dB, no issues there. As you've seen, I've also put the Oled display into the box. It's nicely supported by the firmware. In the down converter, there is an I2C interface, and I can recommend this 3D printed frame. It makes it very simple to mount this display onto the box. There's 2 pieces. You put the OLED display into this bigger piece, and then you put the second part on the back, and then you can screw it to the front plate of your up converter or transverter. The design is by Thorsten Godau, the Delta Lima 9 Sierra Echo Charlie, and if you want to get it printed for little money, Alfred Pertler, Delta Lima 3 Mike X-Ray is providing some printing service. You can find the data also or publicly, the printing data. The potty feed I modified a little bit because I wanted to put it in a nice encasing to shield it against any weather influences. The Opticom LNB, therefore I had to modify. I don't use the original ports for narrowband and wideband / vertical horizontal output, but I put thin coaxial cables inside because my tube, which I'm using, has a diameter which doesn't allow to mount the connectors here. But it's very simple. Put off the lid and you can connect such thin cables here. On the cable, just make sure it has good shielding. The insertion loss really doesn't matter because we have so much gain in the down converter in the LNB that even if you lose here on a short cable 1 or 2 dBs, it doesn't really matter. We have, I think, more than 60 dB of gain. Here you see the potty feed with the lens mounted. This ring is just to shift the whole setup into the tube. I'll show you some pictures later. You can see here an adapter from the waveguide to the input of the LNB. A friend of mine has machined that. It's made from brass and it's soldered onto the copper waveguide, the circular waveguide, and then it has a taper inside, so it makes a transition from the slightly larger diameter of the waveguide of the potty feed to the thinner diameter of the LNB. So there's a taper, and this brass piece goes into this into the waveguide of the LNB. It's then screwed down and firmly attached, and yeah, it works pretty well. Here you see some pictures how the potty feed is mounted into this standard HD pipe, and I can really recommend the Venton Rocket LNB lens. Those LNBs are very cheap. I think 5 or 6 euros. Just buy the whole LNB. It's DRO stabilized LNB, so not really recommended for use here, especially on narrowband transponder. But I just used the lens of it, which are 2 pieces, and glued it here on top of the front of the potty feed. For portable operation, typically I leave it open, but for permanent, I have also Teflon cover. It's a Teflon foil with a ring, and it can be plugged onto the tube. The tube is mounted so that the opening is at the lower part, so no water can ingress. On the back, you see the outputs, the TX input and the 2 outputs for the down converters. This is shown before I sealed it. Typically, I use Spinner Plus 2000 to seal the connectors, and that makes it waterproof. And inside, you see the connection cables, which are then plugged into these cables you've seen coming out of the LNB. Respectively, here is an N connection going into the transmit port of the potty. The potty feed shows a very nice match. The input return loss is about 124 dB. The Whiskwa is about 1.14. So pretty nice match. You can also see here, this resonance is actually the effect of the potty, where we have a longer side here and a shorter side here. And this really generates the circular polarization because we have a resonance slightly above the 2.4 gigahertz and slightly below and slightly above. And at 2.4 gigahertz, those 2 resonances combine and you get the right phase shift to get the circular polarization. This is the setup now in my backyard. I'm using a 60 centimeter offset dish from Kathrein, and you can see the arm for the feed is mounted upside down, so there was no water coming in. and also the transverter is mounted here on the back. It's actually also giving a pretty good balance of the whole setup. I'm using a battery for the portable operation with the small solar cells, which is buffering it, and an IC 9700. I started using SDR from the beginning on QO-100, but I have to say it's really fun also operating outside and without the need of a PC, and just use the IC 9700. It's really fun. You can see here on this picture the transverter mounted on the arm. You can see here a small bracket with the GPS patch antenna mounted on top of it. And yeah, so there's actually no interference because the main beam is going out here. I haven't seen any problems with the GPS antenna being influenced by the transmit signal of the up converter. Nice thing about this Katrine dish, actually I found it on the scrapyard here, in the local scrapyard, cleaned it up a little bit, and it has here 4 screws which you just loosen, and then you can see it here in more detail, and then you just can easily remove the dish from the mount, and for storage and transportation. Also, I have used one of my tripods from my telescopes and just made an adapter, and also just losing 3 screws, and easily the whole thing is disassembled. This is a picture of the received signal using SDR console. You can see the beacon signals here, the PSK beacon here, and actually you can see even the signal Mario mentioned, the leakage of the Bluetooth very slightly here. So the setup with the 60 centimeter dish is amazingly sensitive. You don't really see the role of the transponder in terms of the transponder noise. So that's a little bit low, maybe half a dB you can see. But also the uplink signal is about, my uplink signal is about 60 dB below the beacon level, which is perfectly fine to make good sideband QSOs. So yes, the 60 centimeter dish, I believe we shouldn't go below, because you should always have a sensitive setup, but it's perfectly okay for using it for portable operation. For DATV, I'm using a mini tuner. This one is actually from BATC, and it's connected on the back of the down converter. You've seen there is an output to the mini tuner, so I can actually also watch while making sideband contacts at the same time with the PC and the mini tuner, watch the DATV downlink. It's at the edge, I would say, because the dish is pretty small. But I show you some picture. You can watch DATV with it if the uplink signals are strong enough. So this is the beacon, the DATV beacon, which we are transmitting from the ground station. You can see the 1.5 mega symbol per second signal QPSK. MER here was 6.1 dB. So the minimum for receiving it is 4.7. So with this setup, I have a margin of 1.4 dB. And here are some examples of some users. This is OE6GKD transmitting with 500 kilo samples, and MER 4.5. You see the margin is very low, 0.5 dB. So if some clouds are coming up or so, you will always already lose the reception. So again, the 60 centimeter dish is really only recommended for portable operation. When we go to lower sample rates, the margin gets higher. Here you see a signal from IW1EF at MER of 6 and the margin of 2 dB, and going lower or at similar margin, HB9DUG with 250 kilo samples of 8 PSK signal, and even 125 kilo samples from ON5 AFB was received with that. So to simplify a little bit the setup, I decided to do something which we actually have done. AMSAT-DL has done similarly in the setup in Antarctica. means reducing the cabling between the transverter and the transceiver. And I modified two triplexers because they have really PL connectors, and I replaced that by N connectors. But essentially, you can route then over the triplexer the receive signal on 2 meter, the transmit signal on 70 centimeters, and the 10 megahertz reference frequency from the transverter to the transceiver. So I run only one coaxial cable here to the transceiver, and that makes the whole setup very easy. Here you see the three signals: the 2 meter narrowband output, the transmit input, and the 10 megahertz reference from the transceiver, from the transverter going through the triplexer into one cable. And in front of the IC 9700, same thing happens. We get the signals here from the transverter and split it up again into those three signals. For portable operations, I wanted to have a simple way to transport it. So I built a wooden box from light poplar plywood. And outside I can easily attach the parabolic dish with the two screws. As I mentioned, very simple. There are the four holes, these oblong holes, and you can hang in and attach and firmly attach the dish to the wooden box. And inside the box, you can see that the whole setup of the mount on the tripod, including the transverter, the mini tuner, and the feed, is all assembled. So I only need to take this out, put it on the tripod, and then hang in the dish with screw tight the four screws for the dish on the arm. And less than 10 minutes, you are ready to go. In the box, there is also space here for the IC 9700. So the whole setup can be easily stored and transported. You can get the down converter, the up converter, which is, has a maximum output power 6 watt, and the modified LNB on the AMSAT-DL shop. And I would like to give a special thanks to Stefan, Delta Fox 8 Golf Alpha Charlie, and Kurt Delta Juliet 0 Alpha Bravo Radio for developing this excellent transverter. And there, sometime soon, we will also have a new N casing for the up and down converter. So if you are a little bit shy on doing the mechanical work, integrating the modules into encasing, we will offer in the AMSAT-DL shop a ready-made encasing with engraved front panel, and all the holes are already in. Even the patch cables are included. So that will make life much easier for the users. And I would like to thank you very much for your attention. And let me check on the transponder and also on the YouTube whether there are any questions.
Yes, Matthias, maybe I can step in because there's one question on the YouTube channel that was about your equipment, if it's all waterproof or is it workable for continuous work outside from HG5APZ. Maybe you can answer that question.
Okay, yeah, thank you very much for the question.
Mm-hmm.
Actually, the dish itself, the feed itself is waterproof. I was running this, I'm running similar feeds also on my permanent setup. The transverter box itself, if there's a little bit of water coming on, it's no problem, but it's not completely watertight. So I'm not running the setup in the rain. Actually, I have a veranda and there's a little bit of a glass over, so I put it typically there. If there was some rain, I just put a plastic bag on top of it. Then you can still use it, because I assume you're not sitting with your transceiver in the rain, and there's only one coaxial cable needed between the transverter and the transceiver, and the length actually doesn't matter. You can easily run also 20 meters. And if you put a plastic bag just on top of the transverter, then you are perfectly fine. Okay, Let me check.
Yeah, okay, well, no more questions on the YouTube channel. Nothing on the wideband transponder channel. So, yeah, back to you.
Good. So thank you, Florian. So we are well in time, and actually it's always better to have a little bit earlier the lunch break. If there are no more questions. And oh, there's a question here. How much current draw of the whole systems? Let me go back on the presentation. Let me see whether I can do that. Mario, can you go on this slide?
Yeah. Just a second. I need to reopen the presentation because I closed it already.
Yeah,
which slide?
MM7 WAB asked about the current draw. And
yeah, which slide do you need now?
It's the slide where you see the measurement of the output power versus input power, and also the current assumption is mentioned there.
Okay, I'll look for that. So it should be.
There's a graph and there's a table.
This one.
Yeah.
Here you go.
So you see, this is the total current consumption without the IC 9700. So it's an up and down converter, full duplex. So at 2.5 watts output power, no, sorry, this is at 6 watt output power. At 2.4 or say 2 watts to 3 watts output power, current consumption is roughly 1.3 amps. And then on top comes your transceiver. The IC 9700 is a little bit power hungry because of the display, and so if you use either the IC 202, 402, or maybe 857, then the power consumption will be lower. But of the transverter with the GPS and the LNB is included, all this included, it's about 1.3 amps at nominal output power. Okay, I think there is no more questions.